Good evening, everyone. I, Dr. Sarika Chauhan, Chair of the Program Committee at EdTech Society and Chief Academic Officer at Vidyalanka School of Information Technology, Mumbai. With a great pleasure, I welcome you all to the Masterclass 18, focusing on scientific design of virtual lab experiment. Before we start, let me give you a quick overview of EdTech Society. EdTech Society is a professional association started in India by individuals who are committed to improve instruction and learning through the use of educational technologies. EdTech Society members are researchers, developers, and practitioners in the field of educational technology. Joining EdTech Society offers numerous benefits: network and collaborate with experts in educational technology, opportunities for professional growth, affiliation with international associations, awards, scholarships, and internship programs, reduce registration fees for annual conference and EdTech Society's faculty development programs, winter and school summer schools. You will be able to access to key resources and best practices in educational technologies. We also conduct various events like Masterclass, Industry Talk, In Focus Interview, Perspectives, a panel discussion, T4E conferences, and many more. So join us and unlock a world of opportunities in educational technology. For more details, you can also visit our website etsociety.org. So now let me introduce our esteemed speaker for today's masterclass, Dr. Anita Diwakar. So CEO at VJTI Technology Incubation Business Incubator. She is an educator at heart and soul, holding a PhD in educational technology from IIT Bombay. She brings over 30 years of teaching, 11 years of industry, and 10 years of research experience. So, with a focus on virtual laboratories, she has trained thousands of educators and students. She has published papers in international conferences and conducted numerous workshops. She is recognized with awards like the Global Online Laboratory Consortium Best Online Virtual Laboratory Award for 2020 and the Best Paper Awards for various research papers she has published in international conferences. She is also a member of professional organizations such as ISTE, CSI, IEEE, IAOE, and GOLC. She also holds key advisory roles at TIH Foundation for IoT and IoE, IEEE Bombay, and Symbiosis International Deemed University, Pune. Additionally, she contributes to curriculum development and educational policy making. Dr. Anita shares her expertise through a YouTube channel focused on electronics engineering education. So, on behalf of EdTech Society, I extend a warm welcome to our esteemed speaker, Dr. Anita Diwakar. Ma'am, we are delighted to have you here today for this masterclass. So, before I hand over the session to Dr. Anita Diwakar, there is an announcement for the participants. You all can post your queries using the comment section, and the answers will be given towards the end of the session. Now, I request Dr. Anita to begin her session. Over to you, Dr. Anita.
Yes, so thank you, Dr. Sarika, for the kind introduction and also sharing the details about the EdTech Society. And a very warm welcome to all the listeners out there. Although I cannot see you all like we see in the physical scenario. So let me share my screen so that I can start the presentation. Yes, so I hope this is visible. Okay, so a very warm welcome once again. So I'll be covering this scientific design of virtual lab experiment in the Masterclass 18. So at the outset, I would like to thank Dr. Sridhar Iyer sir for giving me this opportunity. All the faculty members at IIT Bombay, then Dr. Briju, Executive Director at Tech Society, Dr. Sarika Chauhan, all the EdTech Society members, and all the participants and listeners. So let me begin today's talk with laboratories, because this has been an exciting place for lot of development over decades, over centuries. So basically there are three types of laboratories: the development, research, and instructional or educational. So development laboratory is a place where the engineers design, develop, and test a new product. Research laboratories are used to obtain broader knowledge about the world, and instructional or educational laboratories, in these are the science and engineering students, they perform experiments to learn for conceptual understanding, to develop skills, attitudes, and so on. Now, these three types of laboratories have many characteristics in common as well as some fundamental differences. Now, today's talk, I'll be focusing on the instructional or educational laboratories. Again, they are of two types, that is the physical or traditional labs. So these are the labs which we have been using since our childhood. So since the school days, we go to these laboratories for performing experiments in say physics, chemistry, biology, and so on. And this virtual labs, again, it's not a very new concept, but yeah, compared to the physical labs, I would say yes, it's a new concept. So the virtual laboratory is an interactive environment for creating and conducting simulated experiments, basically a playground for experimentation. So it consists of domain dependent simulation programs and experimental units called objects that encompass the data files and tools that operate on these objects. So it's like a playground on the computer screen where the students can play around with the whatever is available and perform various experiments. Again, the virtual labs, they are of two types, that is the simulation labs and the remote triggered labs. But today's talk, I'll be discussing mostly on the simulation type of virtual laboratories. Now, many times, people have a confusion, right? What is the difference between simulation and virtual lab, right? So basically the science simulation software, if you see, they fall into two categories, that is the virtual laboratories and simulations of scientific phenomena. So virtual laboratories, they simulate on screen the experiments that are traditionally performed in real school laboratories as part of biology, chemistry, and other science subjects. Nowadays, even laboratories are available for mathematics and other courses as well. They provide opportunities to use virtual materials, equipment, and tools that are designed to replicate those in an actual laboratory. So virtual lab basically is something which is a replication of the physical laboratory. So whatever resources are available in the physical lab, all those resources should be available in the virtual labs as well. So this particular picture that I am showing now is a simulation of a scientific phenomena. So if you see, this is the scientific phenomena that we call as the resistance, right? So resistance, it depends on three parameters, that is resistivity, the length, and the cross-section area. So it is directly proportional to the two parameters, that is resistivity and length, and inversely proportional to the area. So in this simulation, the learner or the user can change the values of these three parameters. So there are sliders available here. There are sliders here, and with the help of these sliders, the students can change the values. And when they change the values, they can see a corresponding change in the resistance. Similarly, this picture also, if you increase the length of this will increase. If you decrease the cross-section area, this area will decrease, and so on. And again, if you change the resistivity, if you change the material, the color of this will change. So this is a very, very basic, simulation of this phenomena. Now, a very advanced simulation, again, this is the simulation of the electronics, basic and advanced electronics. So this is simulation software for this particular course. Now, if you see, most of my examples that I'm going to cover today belong to electronics, because I have been in this domain for almost now 30 years. Most of my experience is in this domain. So if you see here, on the left hand side of the panel, so this is the place where the students can play around, right? And this is the workspace of the students or the learners. And then there are these components and equipment. So there are some basic equipment, there are some advanced equipment like the resistor, capacitor, inductor. Then there are these sources of like the AC source, DC source. Similarly, there are some meters available. So if you click on the advanced, there will be like meters, then there is an oscilloscope and so on. So whenever the student has to construct the circuit, he has to press on this build and then drag these components and the equipment and then connect. Now, whenever the student is or the learner is constructing the circuit, he will be getting prompts here on the right hand side. So if he misses or some component or some, there is a wrong connection, then he immediately is given a prompt here that you need to change the circuit or you need to add value of your component. So all the prompts are available here. Then there is a run button here. So when the user presses this run button, actually that particular circuit diagram is completed, and if it is a meter that is connected, the value is displayed. If it is oscilloscope, then the waveform is seen, and then that for actually observing the waveform, the user has to click on the analyze. Now this is a simulation, right? Now if you just give the learner this particular simulation, obviously he is not aware of what exactly is supposed to do. So there comes the virtual lab experiment, right? So to qualify for a virtual lab experiment, the simulator obviously should have all the components, devices, equipment, so that the students can play around like in the physical. And along with that, there should be a well-designed experiment that can be performed using the simulator. Right? Unless there is a well-designed experiment that the learner can perform, we cannot say that it is a virtual lab experiment. And then a set of such virtual lab experiments together then becomes a virtual lab, right? So what are the elements that convert a simulation into a virtual lab experiment? So basically a well-designed experiment. Now when we say experiment, so let me take you through some virtual labs which are available online, open source. Okay, so let me take you to the tabs that are already opened so that you can immediately see this. So Merlot, they have these these are the simulations, right? And there are some labs also. Similarly, the MHRD has, under this National Mission on Education through ICT, they have developed some very good virtual laboratories, and these laboratories are available on in all the engineering domains, right? So I just clicked one of that, and this is the again electronics experiment, that is the color code of resistor. So here in the simulation you can have these, change the value of the resistance. So I'll just enter the resistance value. So the learner has to see the color code, and based on that, he has to enter the value. I'll just select some random value and some random tolerance and then check the answer. So this is an incorrect answer. So you can just show answer. It will give the correct answer. Again, this is a simulation, right? Again, this Amrita University, they have come up with online labs for school experiments. So again, here there are multiple virtual lab experiments that have been designed and developed for school curriculum. Then this is the Go Labs. Again, this is a open source, content which is available. And when you click on this particular content, you can see this. Again, this is a simulation where You can choose the value of the resistance, you can play, you can pause it, then you can reset, you can again change the value of the voltage and so on. So again, this is and if you just want to see the circuit diagram, you can see it, right? Then this is the conventional current and this is the actual current. Now, very recently, I came across this initiative again of the Ministry of Education, where they have developed this Jigyasa portal, where there are virtual labs available, right? So this is again a simulation. If you just see, here there are some prompts that are given to the user, and then he can select the experiment, right? So it's just, the user just has to click on this and he has to follow the instructions. So the instructions appear here, and then he has to follow these instructions. So select any ones. And then there is a prompt that is given to the user, right? So based on that, he can just, perform this. Okay. So this is the, again, I would say this qualifies as a simulation, right? So these are the various simulations that are available. But in case of this, I'll just click on the basic electronics. So here, if you see this is a list of experiments. So if you click on a particular experiment, so now I would say that this is a virtual lab experiment, because along with the simulation, so simulation is a part of this, right? Whereas there are other components also present in this particular lab. So there is a aim, that is the objective of the experiment. Then there is a theory behind that experiment. Then also there is a small pre-test. So there are a few multiple choice questions. Then there is a procedure that the learner has to follow when they are using the simulation. So this is the forward bias. So there is a procedure that has been given. So this user can select, right, the resistance value, the DC voltage, then they can add to the table and plot, right? So the plot will appear here. So again, the learner can go back again. He or she can perform some other simulation experiment. So this basically, I would say, it qualifies as a virtual lab experiment, because it has a well designed experiment components that are going along with the simulation. Okay, so now back to the presentation. So these are the various links that I covered here, out of which some were just simulations and some were the virtual lab experiments. So now if you see, so now I'm showing you the slides which cover basically how the laboratory manual. So when a learner goes to a traditional lab or a physical lab, right? So there is an instructor, there is a faculty member, and he's provided with a laboratory manual. And on the table, there will be the equipment and all the components, everything plays on the table. And also the students will be performing that experiment in group of 4 or 5, right? And this is how the laboratory manual looks like. So again, there is a aim, apparatus, circuit diagram, then there is a theory, then the procedure for input characteristic, output characteristics. Then there is an observation table that is provided to the learner, and then he has to perform that experiment following the procedure that is provided and come to some conclusion and also plot some graphs. So that is a standard method that has been followed for quite a few years now, or even decades. So now what happens is the virtual lab experiment designs that we saw just now also are following the same methodology, right? So there also what is happening, because it has to be a replication of the physical or the traditional laboratories, these laboratory manuals have been converted into corresponding virtual lab experiments. So there is a theory, there are objectives, Then there is a procedure that the learner or the user has to follow. Then there is these, this is what I showed you just now. So there is this circuit diagram. So this is available in the physical lab in the form of actual physical components and equipment. So there's a transistor, then the power supply and the meters, right? So in the physical, these are available as physical components and physical equipment, whereas in the virtual lab, they have converted that into images of those corresponding equipment and the components. And then there are these observations and the controls that are provided. And this is the place where they can plot the graph. Right. So similarly, this is the second part of that same experiment, that is the output characteristics. So this is the simulation for the output characteristics. Now, so this type of laboratory experiment, the strategy, it is called as a expository instructional strategy. So this type of laboratory instruction, it is called as a expository, where you have these aim, apparatus, theory, circuit diagram, procedure, observation table, result, and conclusion. But there has been, after a lot of research by various, researchers across globe, they feel that this type of instructional strategy, they refer to as a cookbook. It's like prescriptive. So it's something like, you are cooking something. So just like it's a recipe for something, right? So the final result, that, okay, at the end of my experiment, this is what I'm supposed to get, right? Like we cook in the kitchen. So we know that, okay, this is the ingredients that we need, and this is how we are going to follow the step-by-step process with these ingredients, and this is what is the final product that I'll be getting. So that's why these type of instructions they are referred to as cookbook. Now what happens with this type of instructions is that, so what are the drawbacks? So what did people find? That because we have been using this strategy for years together, what is happening, right? So what is happening is that, obviously it's not a totally useless type of a strategy. It's not a criticism that I'm doing, but it's something which we need to ponder, which we need to look at, right? So cookbook nature, it emphasizes following specific procedures to collect the data. Then no attention is given to the planning of the investigation or interpreting the results. Similarly, majority of these these experiments, if you see, they operate at the three lower levels of Bloom's taxonomy, that is the recall, understand, and apply. So if these learners, they use these laboratory type of instructions, at the most they can go up to the apply level. So very few laboratory experiments are designed which take the students to operate at the higher cognitive levels of analyze, evaluate, and create. And it has been found that, I think this has been debated quite a few times, that the students, the learners, they lack these cognition levels of analyze, evaluate, and create. So now so after going across these laboratories, after coming across these type of comments, we now like to ponder that, so what exactly is the purpose of laboratory work, right? So ABET is an international body, and they came up with these laboratory learning outcomes. So according to the ABET, these are the 13 learning outcomes that the learners need to achieve if at the end of the laboratory courses. It's not like one laboratory course having all these, but whatever laboratory courses they undertake in their graduation program, these are the learning outcomes that we expect from the learners, right? Now, if you just look at the instructional strategy or the type of instructions that we saw, that is the expository, if you see, the creativity is missing. Then similarly, design is missing. So experimentation. So we are giving them a ready-made experiment. So naturally, they are not able to come up with, or they are not able to develop this skill of how do I do an experiment, or what is it that is required to set up an experiment. Similarly, so most of these aspects are missing if you consider the expository type of a strategy. Even this, if you go if you read thoroughly this NEP 2020, this has been in discussion since quite a few years now, and people are seriously looking into the NEP. So I just took some very interesting points from the NEP 2020. It says that experiential learning has to be there, then learning outcomes including increased creativity and innovation, then critical thinking, higher order thinking capacities, problem solving abilities, teamwork, communication. So emphasis on conceptual understanding than the rote learning, right? And so creativity and critical thinking needs to be encouraged, right? So looking at this, and then also there is a mention of virtual labs there in the NEP document. It says that the existing e-learning platforms will be leveraged for creating virtual labs so that all students have equal access to quality practical and hands-on experiment-based learning experiences. So even the NEP document says that it has to be quality, practical and hands-on, and also it has to be learning experiences which will naturally target these skills among the learners. Now what happens is that resource, so when I normally as part of my research, also after I graduated from IIT Bombay, I carried out a lot of workshops with students as well as teachers, and then I used to ask them, the teachers, that which of these resources you use for designing of the experiments. So when I first asked whether you design your experiments, so most of the institutes or most of the colleges, they have been, these like I mentioned, these laboratory manuals have been, created, and the teachers have been using these over the years. So as the curriculum changes, they do make certain modifications in their experiment designs, and for that they are referring to these application notes, websites, and other university lab manuals. Then some also use the global universities, they also have some content available online. Then obviously the subject theory knowledge and the research articles. So these were the resources that majority of the teachers, they have been using over the years for coming up with their experiments or the laboratory work. So this led me to thinking that why not, and also I found that there is no standardization, right? If you go from, so I have been working as examiners, external examiner, going to various institutes across Mumbai. So I found that there is no standardization that is happening. See, theory, when you talk about the theory, the curriculum is given. But when you look at the curriculum, although laboratory is a place where most of the learning happens, right? So there is no standardization and there is no specific methodology that the teachers are following in order to design the experiment. So that is how I came across this. So I also did a lot of literature, research, and then I came up with this 5-step scientific experiment design process for effective student laboratory experiences. Now, some of these are valid for physical and traditional, but some I would say are valid for only virtual laboratories because of the constraints that we have on resources when we talk about the physical and traditional. So the first step, so these are the 5 steps. So it's a systematic approach towards designing of experiments. So the first step is selecting the broad goal. So what exactly you want to achieve out of this experiment. Then formulate the learning objectives. So aligned to this goal, you have to formulate the learning objective and then decide the instructional strategy. So depending on what exactly is the objective that you are trying to achieve through the experiment, you can decide on the strategy. It need not necessarily be always the expository. There are other strategies which have been well established, which have been well tasted all across, and they have been found useful for achieving the learning objectives. And then obviously once you decide the strategy, the tasks that you ask the students to perform should be aligned to this particular strategy. And then the assessment. So actually this assessment, the design of task and assessment, they go hand in hand, right? Because if you are asking a student to perform a task, then what is it that you are going to assess from that particular task? So these two go hand in hand. So the first, so select the broad goal of the laboratory experiment. So it can be any one of the four. So whether you want to impart some knowledge to the student, or you want to develop a skill in the learner, or a cognitive ability, or some attitude that you also, right? Again, when you talk about the knowledge, that whether it is in the cognitive, that is knowledge based, three domains, affective or psychomotor. So depending on what is the broad goal, your learning objective will be aligned to that, right? So again, yes, so the broad goal, if it is a knowledge, then what level you are targeting, whether it's just remember, understand, apply, or you also want to take your learner to the analyze, evaluate, and the create level. Then if you want to develop certain skill, so like practical skills, the manipulative skills, or the inquiry process, or some ability like logical reasoning or computational thinking or problem solving. So naturally, if your experiment is targeting something like a problem solving, and if you are designing your experiment with an expository type of a strategy, it is not going to work. Like there is no alignment between the target goal and the strategy that you are using in your experiment. So the second step, that is the learning objective. So obviously this again has been well tested, and we have designed so many experiments using this particular formula for the learning objective. So you should start with students will be able to, this is true for even the theory courses. Many teachers are following this particular or learning objective definition, right? So make a decision regarding the cognitive level. Then obviously the cognitive level of remember is not chosen for a laboratory experiment, because it's something because when you are designing the experiment, especially a virtual lab experiment, then you are going to have be doing a lot of back end activities, right? Like coding and all. So naturally you won't target the remember level. So you try to target the higher cognitive levels, and then choose the action verbs appropriate to the cognitive level. And most important, it has to be aligned to the broad goal of the experiment. So these are some examples. I think most of you must be aware of these. Bloom's taxonomy is very old, and people have been using this over so many decades, and it's again a well tested and well established concept, right? So use these action verbs. So now we come to, if not expository, then what are the other strategies? So after a thorough research, I found that these were some of the strategies which have been used by instructors across. So expository is one. Then there is inquiry, discovery instruction, which is also called as guided inquiry. Then there is a structured problem solving. Then a problem based instruction and a project based instruction. Now, after going through this, I added from my experience working in the laboratories, I added this expository with active learning tasks, right? So just tweaking the expository instructions up slightly, adding certain tasks, you can take the learner to higher cognitive levels. That has been, that I carried out some experiments with students as well. So these actually these strategies, they differ in the degree of openness, the nature of students' involvement, and the level of students' involvement. So based on these three parameters, so if you consider these strategies, there is a difference in these three things. That is the degree of openness, that is how much are you giving to the student, and what is the nature, like at what level are the students getting involved in that particular experiment, and what is the level of the involvement of the students. So this is an open-end question to all the teachers out there. So which of these instructional strategies are used by teachers to design the experiments? So if you have not used any of these, I would recommend that you use these, and these are really very, very exciting type of instructions and very exciting learner experience that you can give to your students. So now one very, very important thing that I want to share here is the cognitive structure of the laboratory tasks, right? So when the students or the learners are learning in a laboratory, basically, they are working in two domains, right? So one is the objects domain and other is the ideas domain, or the so when student performs a particular task, that is action. So action is a part of the active experimentation. So like I showed earlier, that when a student is dragging the components from the place where they are available to the workspace, right? So they are carrying out some action, right? Now there has to be, so the other domain is idea. Now when the student is performing this action, is he, at the back of his mind, is he thinking that why am I using this component, why am I selecting this particular resistor, or why am I choosing a DC supply, not a AC supply, or why the value of this resistor that I have chosen is this, right? So it's very important that when they are performing a laboratory work, the establishment of the link between these two is very, very important. It is this linking of the two domains that actually helps the learner to go to higher cognitive levels of learning, right? So like when we say the object, so the student is using that object or observing it, or making the circuit or displaying something, right? So this is the domain where the student is performing some action. Now he is like reporting, like what is the value of a resistor, that is reporting, right? Or identifying that, okay, out of all these resistors, why should I select this particular, or out of all these diodes that are available, why am I selecting this particular diode, or why I'm selecting these internal parameters of the diode, right? And then when they are exploring, right, so what are the different types of equipment that are available, why should I, so again when they are testing something or they are determining a value of something, right? So when these things are being done, that is where they are reflecting on their action, right? So now normally what happens is, when the students are performing the experiment, they most of the time they are just working in the action, that is they are just performing the task without thinking about the why they are doing that particular task, right? So now this is what I have proposed. So what do I do to achieve this linking in the learner, or what modifications are required in the laboratories for achieving this linking, right? So it's a very very basic and a very simple thing that can be done. Like even in the expository type of a methodology that you are using, in order to link this, we can just have something like a student performs the task and you ask question aligned to that task. Now why I said that this particular change in the methodology or instructions is possible in case of virtual lab, because in physical labs, when they are performing the experiment in a group of 4 or 5, you don't know which of the student is actually going to answer that question. So we don't know which student is actually linking the two domains, right? But in case of virtual lab, because the student is on his own, he is in front of the simulation, and there are the simulation has features which allows the student to perform that task. And then there can be this question can be written on a piece of paper as well. It's not necessary that there has to be a separate, although some virtual lab developers have come up with a space where the students can write the answer, right? But it's okay, like I mean, when you are asking this question, so the student is able to link, okay, I'm using this resistor, I'm dragging this resistor, I'm using this value of the resistor. And when you ask the question why, then he is able to reflect on this particular task that he has done. So this action reflection, this sequence of action and reflection is very, very important, and that is which that is what helps him, link these two domains. So this is one example again from the electronics. So construct a circuit for forward bias PN junction diode. So what the students do, they drag and drop diode, drag and drop resistor, ammeter, voltmeter, then the DC power supply, connect the components as per the given circuit diagram, and the construction of the circuit is complete. Now, how do we now connect the two? So what we can do is think and write why each of the equipment is connected. Or there can be some other question. There can be a question even after the drag and drop of diode. What is the value, or which type of diode have you selected? Why have you selected this diode? What is the objective of your experiment? Then why you have chosen DC power supply, not AC? So these are the questions which you can ask, and these questions can lead to the linking. So the third step, that is expository with active learning, discovery, well structured problem solving, and so this is a third step, that is decision about the instructional strategy. So before this, I shared with you the expository with active learning task, where you are asking them questions and they are answering along with the performing of the task. So next we will go to the, so I'm going to take only one out of these five, that is remaining three, that is well structured and problem based. So just one strategy which is a very interesting one, that is discovery or the guided inquiry. So when you're designing your experiment use for this particular strategy, then it has like these four phases. So what is phase one? That is the initiation. So the initiation phase is the first phase in all levels, where this is designed to stimulate and motivate the students' curiosity through questioning, right? Then second phase is questions are eliminated or narrowed down to those types of questions that students can actually answer through experimentation or research, right? So first we have we stimulate the and motivate the students' curiosity. Again, there will be questions. So this is a sequence of questions. There will be no any prescription there, but questions that the students has to answer. Then third will be the experimentation. So here again the students collect data and information and then formulate a method of present. Here again there can be multiple questions, right, when he is performing that particular experiment. Similarly, the final, that is a phase 4, is presentation, and this is the last phase where so in case of virtual lab, it has to be individuals, where they decide on some presentation methodology that they are going to use for presenting their results of their experimentation, right? So here I'm giving again an example from electronics. So in the first phase, so see, if you see expository, it was like aim, theory, procedure, observation table, and so on. Whereas here there is no such thing, right? So here there is just a series of questions that you are going to ask, and the students has to answer those. So just display to, just to motivate them, just to, increase their curiosity. So just put some pictures. So I've put some pictures of the diodes here, right? So have you seen these components? Can you identify them? What are these used in electronics? So now what happens here is that each student might have seen this component in different context. So he might come up with some different, use that he has seen himself, right? Then in the second phase, what you do is find out one application of this component and draw the circuit of that application. So you're not, giving any ready-made solution here. You're not giving a ready-made circuit diagram at all. So again here, you're not telling them what input should be given, what is the output that you expect. So ask them to draw the circuit for that application, which you feel is appropriate for this particular component. And then what output do you expect from the circuit? What did you do to find the application? What happened when you gave the chosen input? Then what could we do to find out the change in output if different component is used, right? So again, these are a series of questions that they need to answer. Then third phase, experimentation. Now what in the previous phase, what they have done is they have drawn the circuit, right, for that application. Now they are going to construct it using the simulation or in the virtual lab, right? Now they will be applying the chosen input and observing the actual output. So what output did you obtain? How is it same or different from the predicted? So here they are saying that, okay, this is the output that I am expecting, right? When I give this input. Now here they are actually doing it and finding out. So is it same or different than you predicted? So here they can, find out, okay, this is what I thought, but now it is, I'm getting, if they're getting the same output, okay, he's able to, find out that, okay, whatever he has predicted was right. But if it is different, then again it makes him think, right, why did I get a different output? Then you can ask, like, what are the characteristics, or is it because of the characteristics of the chosen component because of which you have got the output different? For example, if you are using a diode as a rectifier, so there has to be certain specific, input parameters or the specifications of the diode that are required for it to act as a rectifier diode. So if the student has not chosen a rectifier diode and have constructed a rectifier circuit, then naturally he will not get the output as desired. So now he will understand that, okay, maybe the component, the value that I have chosen, the specification that I have chosen is wrong. Then again, yes, so can you explain why your results do not match? Yes, here we can also ask them to, compare with the peers if they are doing it together, right? Or even otherwise at offline, they can, ask that, okay, this is what I did and this is. Now, what is the advantage of this virtual lab is it is available to the learners 24/7. They are not restricted by only one experiment in that particular time slot, like in the traditional or physical. So they can keep on performing this experiment, they can keep on experimenting with different circuit diagram, different inputs, different outputs. So it's like, it's a whole lot of exploration they can do on their own and learn on their own. Obviously some kind of help is required, so for that, normally along with the simulation in a virtual lab, there is some guidance that is provided along with this, right? So there are some PDFs or some content which is available to the student in case, even after multiple attempts, if they are not able to get the answer, then they can look at it, and the instructor also can provide these, right? So with this, I have completed this guided discovery or guided inquiry. Now I'm just showing another strategy which I have used myself. So all these strategies I have used with students, and they said that this is the first time that we are doing an experiment like this. So obviously there were some problems that I had to encounter, but at the end of the course, like whenever I used to take this as an audit course in some colleges in Mumbai, so at the end of the course, when I took a feedback, they were really, excited that, okay, this is, they said that, yes, it definitely helped us learn more than what we had expected out of this virtual lab course, right? So this is a strategy which is a structured problem solving. So normally, the students do solve these problems in the theory class, right? So in the common emitter, so these the values are given and VCC is given, construct and obtain the DC characteristics, and then find IB. So these values normally the students are able to find with the help of standard formulae. So in this experiment, what I have done is, so theoretically also they are finding out the values, and they perform the experiment in the virtual laboratory or on the simulation, and they find out the practical values as well. And then they are asked to compare the theoretical practical and also compare with your neighbor. So this also was very helpful. So this is a structured problem solving. So problem solving can be, given as an experiment, as a virtual lab experiment. Then similarly, this is again another design that I had given to the students. So this is from the digital electronics course. So this is actually a real world type of a problem where a bank has 3 locks with a key for each lock. So each key is owned by a different person. In order to open the vault door, at least two people must insert their keys into the assigned locks at the same time. So the trainee, that is person 3, can only open the vault. So these are the conditions that are given, right? And based on this, they have to come up with a logic, right? So they have to come up with a truth table for the digital locking system. So this is a digital locking system, which is a real life problem that has been given. And then they have to come up with a truth table, right? And then using, so they were asked to design using the K-map techniques, a minimum and or gate network to realize the locking system. Similarly, implement this using two NAND gates, two NOR gates, right? So these are called as the universal gates. So now first they are asked to do using AND OR gates, then using the NAND and the NOR gates. Now, again, these specifications are given. So which of the locking system is the fastest? So if you are saying that, okay, I have implemented all the three, the same logic using the three different combinations. So out of this, which is the fastest? So they have to now calculate, right? And obviously, when we say that, it's a digital lock, it has to be fast, right? So they come to know that, okay, if I implement using this may be a problem, this may be slower, and this may be faster. And so this is basically the ill structured problem solving scenario, that or the strategy that has been used here. And this again has been given to the students, and they have been able to come up with the solution very fast. Meanwhile, these students are very smart. They were able to do this in 1 hour slot that I used to go and conduct the experiments. And what the beauty of this was, the different students, they came up with different implementations. And then they found that, then I actually awarded the student whose implementation was the fastest of all the different implementations. Now the final step, if you see in the laboratory assessment, is design is the assessment. So this is a very, very, comprehensive topic that I think it needs another 2-3 sessions that we can cover. So what is it that you are assessing through this particular experiment? So are you going to measure student knowledge, skill, cognitive ability, attitude? So if you are going to measure the knowledge, then at what level? How are you going to check, or how are you going to assess whether that has been achieved? So that is a very difficult thing. So your assessment questions have to be aligned to your learning objectives. And also, if you are trying to develop a certain skill, then there has to be certain rubrics that have to be developed. So yes, obviously there were some rubrics which I had developed as part of my research. And then similarly, whether it's going to be just a formative or summative. So most of these current laboratories, they have the summative, where there is a pre-test and a post-test, and most of the questions are aligned to the theory, right? So formative is something which I shared, like, you have asked them to perform a task, ask a question, and then depending on the answer, you can give some points to that, and then some badges, and that whole lot of thing that can be done for the assessment. And then instruments can be different. You can use those different instruments for coming up with the assessment. So that's all from my side. I hope I am on time. And yes, so right on time, I think. So over to you, Sarika. I think we had planned that at the end of this, we will be covering if there are any question answers. So a very thank you, everyone. Thank you for your patience. I hope I did not put you to sleep, like I always say. Yeah. So
No, no. So we have Dr. Anita. So, okay, let me start with the questions posted by the
sure,
participants.
sure.
So, there is one question from Saurabh Mehta, like how to develop virtual lab.
Okay, so see, there are two ways of looking at it. So, if you really want to start from scratch, so you have come up with your design, like following this step by step process, you have come up with the design of your experiment. So there are two ways. So if you already know some simulation which already is there existing, like from the repositories that I've shared, so you can take that. They allow the embedding those simulations in your software. So that is possible. And then normally what I suggest is, for development, people have used, over the years, they have used some very high end software like MathWorks, and a lot of software are available for coming up with
Okay.
the simulations and other. But what happens is that it's very difficult when it comes to the user part. So I recommend that you develop the virtual labs using very very basic, tools that are available. So most of the virtual labs that we have developed, like I think along with you also we have developed the virtual, so we
Yes.
have used, so it's like, browser based, so that the learner, he just clicks on the lab experiment and he clicks on the simulation and the simulation can be seen. So it's like a browser based, so you don't have to download any software, you don't have to install anything on your end, because if those steps are involved, then it becomes, a bit difficult from the user perspective. And when we are talking about, users doing it on their own at their, pace, in at their home as well. So it's very it's good, it's a good practice that you have these browser based experiments, so that it is
Okay.
easy for using the. And then yes, for
Gotcha.
browser based we have used HTML5, JavaScript, and so these are the basic, very basic things, and they're powerful. Like, we can develop some very good laboratories using these tools.
Okay. So basically, the web technologies we can
Yeah,
use
yeah,
for
that's true.
developing the virtual labs, which should
Yes,
be the
yes,
web browser
absolutely,
based.
absolutely, yes, yes.
Okay. Anita, there is one question from Shrunika. Is it free to use? Like when you are displaying, right, all the list of the virtual labs. So are all those are free to use? Like user can use it freely, or
Yes,
any login
yes.
or anything is required?
For some, I think there are they have these login and registration and all is required. But most of the labs that, or most of the simulation that I shared, they are, open source. Just a small registration might be required, wherein you share your name, email address, and so on. That's it. That's it.
Okay. So there is one last question from my side. Can you provide more information about the Gold Best Online Virtual Laboratory Award, which you have received in the year 2020? So if the other people, those
Yeah,
who
yeah,
are
yeah.
actually working on the virtual lab, how to apply and what was your, area for that, those
Yes,
particular,
yes,
especially
yes.
for
So
this particular
I'll be
award?
happy to share this. So just excuse me. So I'll just maybe my screen is shared already, right? I mean, I'm sharing the screen,
No,
no?
no.
You can't
You
see
have
that?
to share the screen. Exactly.
Okay, okay.
Yes, we can see that now.
Yeah, yeah. You're able to see?
No, no, you just have to share it again.
Okay.
Yes, it is
Yes.
visible now.
So this is International Association of Online Engineering. So I'm a member of this IAOE. So this is a community of people who are, excited by this concept of virtual laboratories and online learning, obviously. And then they have these global online laboratory consortium. So if you see, the
Okay.
mission statement is that creation of shareable online experimental environments which increase the educational and scientific value of learning, which may not be accessible, scalable, or efficient through traditional methods. Right. So if you see the members, so all the, global universities are members of this association or consortium, right? And then every year they have these online lab award, GOLC online lab award. They announce it through this portal itself. So here you can see the announcement happening every year. So around the month of September, October, they start the announcements for the awards. and then you have to apply for that. They provide you with once share your interest in participating in this award, they will send you over email the details about that award, and then you can submit your proposal for the award through the email itself. And they have this again, there is one conference that they conduct every year for virtual instrumentation. So REV, that is remote and virtual instrumentation, that is the name of the conference. So you have to register on that particular portal of the conference, and then this is the award call for 2024 that was done, and these are the winners. And I'm very happy, actually it's something very exciting for me as well, that see, I sent my proposal in 2020 for the machine learning lab. So you can see here,
Okay, it was a machine
this is
learning
the
lab.
machine learning lab which I
Okay,
developed along with students from Somaya College of Engineering under Mumbai University. And then
great,
next year, optical fiber communication, again, a entry from India. This was from Vivekanand Institute of Technology. Professor Ranjan
great,
Bala, she submitted her proposal. Then 2022, we did not see any winner coming from India because of maybe the COVID, and we were like, stuck in the pandemic and all. So, but again, 2023, if you see, virtual lab in oscillator. So this is again by Professor Rasika from Vivekanand. And I'm happy to share
great.
that all these, professors, they have uh, use the guidelines for the design and development. I have conducted workshops for them for the design and development of these virtual laboratories along with students. So they develop.
Great.
So
It was
yeah. So the as a domain expert, the faculty members were involved, and then there were students who were experts in the web technologies and programming and all. And I think Saurabh, Professor Saurabh, also has received this award, which will come as soon as they this this was the award call. And he shared with me very recently that his lab has been selected for this award as well.
yes.
Yeah, so
Great,
it's
great.
very exciting space to be, and the possibilities are infinite if you look at the
Yeah. So
virtual labs. And now I have discussed only simulations. Right now, people
okay.
are using some very high-end technologies like the virtual reality, then the augmented reality. So with this, it's limitless. The
Yes.
opportunities are
Great.
endless and the learnings are limitless. So it's a very exciting space to be.
Yes, that's great. Okay, so we don't have any more questions. So, as we come to the end of this insightful masterclass, I wanted to express my heartfelt thanks to each and everyone for their participation and engagement. My sincere gratitude to Dr. Anita Diwakar for accepting our invite and for sharing her valuable insights and expertise with us. Your contributions, specifically the five-step scientific experiment design process, for effective student experiences have enriched our understanding about the virtual labs in the education field. So, successful conduct of this event wouldn't have been possible without the strong support and guidance of our mentors, Sridhar Iyer sir and Viju sir. And special mention to our technical team members Vivek Sabanwar, Nagesh Portle, Sandeep Yadav, and Ramdas Rai for their invaluable efforts. So, thank you everyone, specifically to our participants. Thank you for your active engagement and thoughtful questions. Thank you once again for being part of this masterclass, and we look forward to your participation in our future events too. I wanted to make few announcement for the participants. You need to attempt the quiz and fill the feedback form, which will be available in your EdTech Society dashboard after you log in to your account to get the certificate for this masterclass. There is one more very important announcement. We are celebrating second annual day of EdTech Society on 27th April at 6 p.m. More details will be shared soon on our website etsociety.org and on all our social media platforms. So we request you all to join virtually and celebrate with us. So thank you once again for being part of this enriching experience. Thank you, everyone. Have
Thank
a
you. Thank you.
wonderful evening.
Thank you. Thank you.